Thank you very much for the introduction. Thanks to the organizers for the invitation. It's great to be here. So this is a lecture series on sharp restriction theory. It consists of 3 lectures. They are a bit longer than usual. And the general plan is to give an introduction to the topic today and to focus on 2 recent developments, both tomorrow and on Thursday. Okay? All right, so let's start. I'll mostly be using the board, by the way, but there are a few pictures that I want to show you, so the slides are up. Let's start very easily with the house of young inequality. I like to think about this as sort of a toy model for some phenomena that show up in restriction theory. Okay, so the house of young inequality is about a Fourier transform. Everybody knows what that is. We start with the function f. That's P over E. B is the dimension, any number greater than 1 is fine, and B is an exponent between 1 and 2. Okay, so if P is 2, we have contrast theorem. So this statement is actually an equality. If P is 1, the Fourier transform of an L1 function is bounded. It's also continuous, uniformly continuous. And the triangle inequality implies an inequality with constant 1. So we can interpolate, we can use Ristori and get Hausdorff-Young for all exponents p between 1 and 2. Okay? So this is the box. This is the Hausdorff-Young box. And an observation by Beckner from 1975 is that a better inequality holds. Namely, this constant 1 can be replaced by a smaller number. I'm going to call it BP. That's okay in dimension 1. In dimension B, I just have to raise it to the big power. And this constant BP is explicitly given in terms of P and P prime by P to the 1 over 2P times P prime to the 1 over 2P. Okay, and you can check that if P is strictly between 1 and 2, this number is strictly less than 1. Okay? Of course, if P is 1 or P is 2, we cannot improve it, but for every P in between, there's this better. Okay, so this was a big breakthrough. The problem had been considered before, and I guess 14 years later, Técnico proved the same thing, but under the rather restrictive assumption that P prime is an even integer. Okay? And even exponents, well, they are special in harmonic analysis because special for inequalities involving the Fourier transform because you can always reformulate this function out, reformulate it in such a way that the hat is gone from the picture. And we'll see this often being the case in sharp restriction theory when exponents are even, we can do that. Okay, so Beckner's proof was quite ingenious and actually surprising at the time. He used tools from probability theory. And one of his conclusions was that Gaussians maximize Hausdorff. Okay, so like here, this equals e to the minus x squared maximizes the Hausdorff inequality, which means that it turns this inequality into an equality. Okay, so that's one example of a maximizer. A few years later, 15 years later, Lee went further and he characterized all maximizers, and he actually proved that all maximizers are Gaussians. Okay. So the standard Gaussian is an example of a maximizer, but of course this inequality has a large group of symmetries. And if you apply symmetries to this standard Gaussian, you get other Gaussians. That's actually what's meant by Gaussian. So this is just a set of functions which are obtained from the standard Gaussian by applying the symmetry of the Hausdorff-Young inequality. And we prove that that exhausts is a complete list of all the ones. Okay, so this is my first time on the board. Almost. So As I said, I would it will be.
Very good. Sorry. So what happens when P is equal to 1 and 2?
In terms of maximizers,
No, the best constant.
well, if P is 2, you have Poincarel's theorem. So depending on the normalization for the Fourier transform, you'll have an identity that's true for every L2 function with constant 1.
So that the constant is actually worse. Or this the square root of P.
Sorry, you're asking about this best constant.
Yeah, correct.
When P equals 2?
Yeah.
P equals 2 is Poincarel with an identity with constant 1.
Is worse than.
This estimate Wegner's is delivering a worse constant equal to
Yeah, but
compared to Plancher's that
square
is
root
1.
of 2 is bigger than 1.
Sorry, I think there's a minus 1 over
Minus.
2P prime.
Yeah, it's a minus.
Okay, so this guy should be minus 1 over 2P prime. And I don't want to correct that because I will have Is that okay?
Yeah.
Yeah, so you should recover B1 and B2 should be equal to 1.
Okay.
Okay. And of course, if P is 1, P prime is infinity, so there's a bunch of conventions. But you want to recover it.
That means that the normalization with the 2 by island.
Correct, because you want the Fourier transform to be an isometric to.
So we always deal with the normalization.
Not always, no. But for the Hausdorffian discussion, yes. Thanks for the questions. Anything else? Okay. So there's one further refinement of Hausdorffian, which I also want to discuss because we'll see how that translates into restriction later on. And this is viewed, this is a 21st century refinement into this. It's on archive from 2014, and that's a sharpened version. So it's also true, it also holds for every dimension, for every exponent P strictly between 1 and 2. And so you start with the maintenance refinement of the Hausdorffian inequality. And what Chris proved was what's called quantitative stability for Hausdorffian. So that's the existence of a constant that depends on P and D. It's a positive constant. And the refinement consists in the missing term. So the missing term is minus a constant times the distance squared. This is the distance in LP of F to the space of Gaussians, which can be noted by script G. And you normalize it by dividing by the algorithm S. Okay. So this is a stability version or a sharpened form of Hausdorffian inequality. It basically tells you that if you're close to being a Gaussian, so if you're a Gaussian, this distance is 0 when we just recover Beckner. If you're close to being a Gaussian, that means this distance is small. And so that means that you're also close to obtaining the best constant in Hausdorffian. Okay, I call this, or this is called quantitative stability because this exponent squared is best possible. A yet sharper version would be what's called constructive stability, where you would have some quantitative control over this constant literacy. That's not the case. Okay, so the argument proceeds by contradiction. You have to, at the same time, know a complete characterization of the maximizers, which you do from Beckner plus Lee, plus pre-compactness of arbitrary maximizing sequences, modular symmetries, which Chris proved. Okay, so once you have these two ingredients, it's sort of a classical route, first observed by Bianchi and Littnell in the context of the Sobolev inequality, to get a stable version of this. The disadvantage, the pay you have to, the price you have to pay, is that you don't have any quantitative control overs. So you have quantitative stability, but not constructive stability. It's still an open problem as far as I know.
And what is the distance?
The distance in LP. Okay, so yeah, to the space of Gaussians, and Gaussians are defined as I defined them above. Okay, so this is what I wanted to tell you about Hausdorffian. Let's move to restriction. Okay, so restriction. This is restriction theory for the Fourier transform. That's what we're talking about. Okay, so the bridge between the two can be made with the following observation. So from Hausdorff-Young, you know that f hat is defined almost everywhere in B, if f is in P and P is between 1 and 2. Okay, that's just a qualitative consequence of the quantitative inequality upstairs. A surprising observation by Lisbon, I believe it dates back to the late 60s, 1967 is the reference I found, is that sometimes f hat can be meaningfully restricted to certain subsets of measure zero, like curved submanifolds. And the key word there is sometimes. Okay. So f hat can sometimes be meaningfully restricted to certain curved manifold, but it's curved is a large keyword. The prime example in the sphere. So x equals this one. This is the example, but it's going to be actually the main example for all of today's lecture. Tomorrow we'll focus on different manifolds. Let's just say vectors in MP of normal. Okay. So the question becomes at least for this here. Okay, so the question is, when do we have a restriction inequality? So when does an estimate like this, so we take the Fourier transform, we integrate over the sphere with respect to the surface measurement. And let's say that we want an LQ prime or LP prime inequality. So this is an LP prime. There's a constant. In principle, can depend on the dimension and on the exponents, P and Q. And we start with an LQ prime function on R. Okay. So when does such an inequality? Okay. Again, you start with a function f, which has some integrability on Rd. You take its Fourier transform, it is a function on Rd, but we're not interested in the Fourier transform with all of Rd. We want to meaningfully restrict it to the sphere. So we just integrate it over the sphere with some LP prime space with respect to, say, normalized surface measurement on the sphere. Okay, and so this is, if this holds, so restriction inequality, we call it R. And of course, there's the restriction conjecture. That predicts the validity of this inequality as long as the dimension D of exponents P and Q satisfy certain conditions. With this choice from LQ prime to LP prime, I believe those conditions are 2 over Q prime should be bigger than D plus 1 over D, and D plus 1 over Q prime plus D minus 1 prime should be greater than or equal to D plus. Okay, so it's known that these conditions are necessary. This is a question of testing the dual inequality, the adjoint inequality, against some relatively simple examples, like a constant function on the sphere or a function that's supported on the small cap on the sphere. We bet that these conditions are necessary, but the question is whether these simple necessary conditions are also sufficient. Okay, so when B is 2, that means we're talking about a circle in R2. This is known, restriction conjecture is true. This was proved in the 1970s. But in higher dimensions, okay? It's an important question. I mean, it sort of sits. We've heard lectures about this last week if you were on available. So this sits at sort of the center of modern harmonic analysis with many links to local smoothing, vulnerabilities, decay, and also decoupling and so forth. So it's really something that people care about. Okay, so a useful special case is when P prime or P is 2. Okay, if P prime equals P equals 2. This is special because in that case, we can compose the restriction operator with its adjoint, and a version of the TT star method allows us to prove the sharps. Okay, so if P is 2, this inequality in adjoint form translates into the statement. This is from Q prime to Q prime, so the adjoint is from P to Q. That's why it shows numerology this way to begin with. This inequality is going to hold if Q is bigger than or lies equals to 1 over B minus 1, and it's the sign policy. Okay, so this inequality is known to hold, has been known to hold since 1975. And this is just equivalent to the P equals 2 case of the restriction inequality. Okay. I'm going to write it. This is the dual form of a restriction inequality, I call it R up here, when P is here. Okay. So one thing I should define is what this extension operator is. Here, have space, so F sigma hat. So remember, sigma is the surface measure of the sphere. So and F is a function on the sphere. So F sigma is a measure on the sphere. It's a compactly supported measure, so it makes sense to define its Fourier transform. And we could do it abstractly. We can also do it very concretely by a formula that involves integration over the sphere of the Fourier kernel against F omega A sigma. Okay. So this is the extension operator. Right? This was the restriction operator. This is the extension operator. And now this starts to get geometric and interesting. One thing to notice, maybe in a different color, is that there's a sort of a tension here in this integral. So you're integrating over the sphere. So we are integrating over the sphere, which is curved. But what are we integrating? We are integrating a superposition of planar waves, which are flat. Okay. So this is flat. And curved and planar, they don't match very well. There's a mismatch between curvature and flatness, which originates cancellation and therefore decay. Right? So there's decay. And one way to see this is already at the level of sigma hat. So if you take your function f on the sphere, the constant one on the sphere, sigma hat is just the Fourier transform of the surface measure, and you can prove in many different ways that this guy decays like x to the 1 minus 3. Okay. You can look at this as an oscillatory integral and just use stationary phase. In the case of the sphere, there's also an explicit expression for sigma hat involving Bessel functions, and those have the asymptotic properties, and those are the problem. So in many cases, you get decay. Right? This decay is, if you want, the quantitative consequence of this qualitative distinction between the domain of integration of the curve and integrand function being a combination of Euler waves. Okay. Right, a few more comments about Stein Thomas. So far I've been talking about the sphere, but as I said, what's really important about the sphere is that it's curved. So if you replace the sphere by any compact hypersurface, of non-dimensional Gaussian curvature, you'll get a similar result. And by similar, I mean really the same inequality with the same exponents. The Stein-Thomas argument is so robust that we can actually make do without some of these assumptions. For instance, hypersurface might not be compact, might be unbounded if there's some homogeneity to compensate for. We'll see that tomorrow. And the Gaussian curvature might be vanishing, identically vanishing, as long as there are some principal curvatures which are non-zero. In that case, we'll get the different exponents, but the spirit of the inequality is still the same. Okay, so that's the first comment. Second comment is that this exponent is less possible. Okay, so 2 plus 1 over b minus 1 is less possible. This is an example of the map, which is actually the same example that tells you that this condition is necessary for the restriction inequality to hold. Again, take the extension inequality and you just test it against the function on the sphere. Here, the sphere that sort of accumulates close to the north pole, and we can make it symmetric. We can concentrate on the north pole of the south pole. Okay, and just do some elementary estimates there. That's what the map looks like. So being best possible means its endpoint. And it turns out that endpoint Stein-Thomas is essentially scaling invariant at small scales. Okay, so endpoint Stein-Thomas is essentially scale invariant at small scales. What do I mean by this? I mean, this word, of course, is not rigorous. The sphere is not scale invariant, so you'll have some trouble there. But if you zoom into the sphere, let's say in a small cap, then it starts to look more and more like a parabola, the piece of a parabola, and the corresponding Stein-Thomas inequality of the parabola on a compact piece of a parabola is scale invariant, and so the estimates you get do not depend on the level of truncation. So actually, you can get a similar estimate for the full parabola, and that has applications to PDE. Right? Actually, this essential scale invariance of endpoint Stein-Thomas makes this inequality very useful and finds applications for a variety of fields besides harmonic analysis and PDE. So this PDE applications we'll see tomorrow. There's also some nice applications to fractal geometry, number theory, and so forth. So fractal geometry involves, for instance, the possibility of restricting to the one-dimensional fractal measures. So those are by Mockenholt in the beginning of the century. And number theory, for instance, a version of the endpoint Stein-Thomas inequality, where the argument is what lies behind Green's proof of Roth's theorem for the primes that Marius was talking about last week. Okay, there's an endpoint Stein-Thomas argument here. Okay, so this was my introduction to restriction theory without mentioning the word sharp. Are there any questions so far? No? Okay, so let's make it sharp. Making it sharp means the sharp and sharpened versions that I presented in the Hausdorff, right? So we're interested in best constants, maximizers. We can find one good if we can characterize them all better. Once we have a full characterization of maximizers, we would like to go to sharpened versions and so on. Okay. And to begin with, I would like to tell you something about, so the main goal of today's lecture will be about sharp Stein-Thomas. But before diving into sharp Stein-Thomas, I want to present a simpler inequality, which I think is also a good toy model for Stein-Thomas. This is an inequality that goes back to Ackland and Hormander from the mid-70s, which involves the extension operator on the sphere. Okay, so this guy, F sigma hat of X, is what we define here. And what we have here, we have an L2 to L2 restriction type inequality. Of course, restriction is not possible on L2, right? We started our discussion around Hausdorff by saying if you take an L2 function, its Fourier transform is no better than L2, so it's just defined almost everywhere. You cannot really restrict it to this. So what's going on here? We are, this, if you want, is a local restriction inequality. The left-hand side, we're not integrating over a whole RV as we are in time terms, we're just integrating over a ball. The ball, say, centered at the origin of radius rho. We are compensating for that by dividing by 1 over rho. And if you want, in the notation of Eric Alfred, his lecture notes in restriction theory, this is a restriction, a local restriction estimate from L2 to L2 with exponent plus 1/2. Okay? And this is only possible because we're just integrating over ball, not the whole RD. Okay, so this is the inequality that Pagman and Formander proved, and they proved it in greater generality. They didn't really care about the value of the optimal constant, but they did prove that for fixed dimension, as the radius of the ball goes to infinity, these guys stay uniformly bounded and they actually converge to 1 over pi as the radius goes to infinity. Obvious question, what's the best constant? Right? What's the value of this AD rho? And I'm just telling you this story because I think there's something interesting there, but I don't want to get into details. So instead of telling you what the constant is, I'll just show you a picture in dimension 2. Okay. So for the circle in R2, this is the value of the best constant as a function of the radius. And this is something I did with Giuseppe a couple of years ago. And by the way, whenever I have dates, these are all publication dates. Sometimes they don't really match archive, so they never match. Okay, so what do we see? We see that, first of all, this recovers Pagman and Formander, right? As our rho goes to infinity, you see that this really seems to tend to 1 over pi, as they predicted. But then there's a somewhat surprising behavior in between. There are these bumps, there are these cusps. The cusps occur at zeros of a certain Bessel function. And this is the value of the optimal constant for each radius. There's a similar picture in higher dimensions, but I cannot show you if you need many pictures at once. Now, more interesting than the value of the optimal constant is the space of maximizers, which of course is not here, but I'll tell you what it is. So on the first bump, not surprisingly, constants are the global maximizers. Okay, and they are the only global maximizers.
Could you repeat?
Yeah, so for the value of the radius on the first bump between 0 and this first 0 of the Bessel function, the global maximizers for this inequality are constant functions. Not surprising. But on the second bump, the global maximizers are spherical harmonics of degree 1. And then the picture repeats itself. So degree 0, degree 1, degree 0, degree 1, and so on. And then there's funny things happening at the cusps, but I won't get there. Now, more interesting than spherical harmonics of degree 1 being maximizers on the second bump, or even bumps in general, is the fact that constants are not maximizers. Okay? You have an inequality that has rotation symmetry, and the only function of the sphere which have this rotation symmetry, namely constant functions, they're not maximizers on a certain region. Okay? So this is called symmetry breaking, because the maximizers break the symmetry of the problem. And we were kind of surprised to find this. And I'm telling you this because sometimes these sharp inequalities, they hide surprises. Okay, so that means that Beckner and Leib's program are completed for that not remember inequality. What about Christ? So there's also a sharpened version of Agman Formander, and we get it in constructively stable form. Remember, it's an L2 to L2 inequality, so if you can get this, it's probably not hard. Okay, so what does the result say? You consider the deficit function, that's just the right-hand side of the inequality next to the left-hand side. Since the inequality holds, this deficit is non-negative. Well, better than being non-negative, there's a lower bound for it. Okay, and the lower bound is phrased in terms of constant, stability constant, times the distance squared from F to the space of maximizers. There's also an upper bound for it. The constant is actually the same as the sharp constant from the previous one, but that's not so interesting. So let's focus on the lower bound. That's, if you want, the sharpened version of Agman Formander. And again, we can ask, what's the value of the stability constant? What's the best constant? Again, we do it. Here's what it looks like on the circle. Okay, so now things are even crazier. There are bumps. When you approach zeros of Bessel functions, the stability constant seems to want to vanish, but it can't because we always have this lower bound. So there's a jump, right? So this stability constant does not even define a continuous function. And in between consecutive zeros, there are also some kinks and points of non-differentiability, which show that sometimes studying these regularity properties for optimal constants and for stability constants are quite delicate. All right, so I guess this is what I wanted to show. I don't want to discuss these proofs. If you're interested, we can talk about it over the break. But I hope I've convinced you that interest in mathematics is born out of asking about sharp and restriction mathematics. Was there a question?
Yes, what the dotted line represent and 0, 1.
Say that again.
The dotted line represent?
Nothing. No. I mean, I just wanted to say that the stability constant when rho is a base of 0 is here, there, and so forth. Okay.
Yeah.
The space of maximizers are also quite interesting, non-intuitive, and quite convoluted, but I don't want to describe them.
You need hope for higher dimension.
Sure, but we have a result in all dimensions. I'm just showing you a picture, but yeah, it's actually pretty similar. It's just that the Bessel functions show, the Bessel functions are different. But let's say the qualitative picture looks the same.
Just curiosity, so for instance, the extremizers are product of, or is something else?
For the
It's a very higher dimension.
sharpened
Yeah.
version or the sharp version already from the last slide?
Anything.
Yeah, so for the sharp version, they are just spherical harmonics
Okay.
of degree 0 and 1 in all dimensions, and then weird things happen at the kinks.
Mhm.
Right. So not products, pure spherical harmonics.
Can I see the first slide again?
Yeah.
And this one half represents in the towels.
Right.
Yeah.
It represents the 1 over rho. The 1 over rho is like
Right.
1 over square root of rho squared, and that's
So you can put the different exponents and make it.
I don't remember the more general things. So these are hypersurfaces in RD. You could consider, for instance, arbitrary spheres, higher codimensional spheres in RD, at which point this 1 over rho becomes 1 over rho raised to the codimension. Okay.
So for that specific inequality.
This is best possible.
Okay.
Yeah. No twiggle of the exponents.
Diego, I'm very naive, so forgive me if, because usually when you have maximizer,
Mhm.
you rotate,
Right.
you get maximizer, yes?
Not in restriction theory. That's one of the points.
Ah,
Right. So one of the interesting things is that these kind of rearrangement techniques and invariance over rotations, they can badly fail, even when we're talking about even exponents. And I'm going to give you a few examples in the actual case. This was Steinholm, but now we do Stein-Thomas, and the same thing will happen. Okay, and that's why this problem. That's one of the reasons why these problems are really hard. Classical techniques just fail miserably. Any more questions? Okay, so now I think we're going to have a relaxing break while I erase the board. I'll erase 4 of them. Well, so now the point will be to do a case study of a sharp Stein-Thomas. And let's say the simplest case where Q is an even integer. That happens, we want any point because that's the scale, the almost scale invariant version, the most interesting one. So this happens when the dimension is 2 or 3. If the dimension is 2, this exponent is 6. If the dimension is 3, this exponent is 4. 4 is easier than 6, so let's start it. And that's the case study for the rest of the L2, L4 on the 2-dimensional sphere in our plane. I'll basically tell you everything I know about that. Supposed to be reading the news, huh?
nothing happened in the
we are in section 4. That's our case study, in which we look at endpoint cycles in extension 4, L2 to L4 on S2. So this is L4 on 3. We're interested in this estimate. So we start with an L2 function on S2, that's a two-dimensional sphere in R3. We take x sigma hat, that's supposed to be L4, and we want to show that this inequality is maximized by constants. Okay, and by doing so, I mean, right now there's different approaches to this problem. I'll try to illustrate all of them, or at least all the ones I know. And I think that gives a pretty comprehensive picture of where the state of the art was. Okay, so this problem, sharp endpoint Stein-Thomas on S2 was first considered by Chris and Shaw. Okay, some 12 years ago, they have a couple of papers in which they try to prove this statement, but they fail. Okay, so they obtain partial progress towards that question. Their first observation is that, okay, since 4 is an even exponent, you can use Poincaré to rewrite the left-hand side of the inequality in terms of a convolution. Okay, so this is equivalent to an L2 to L2 inequality for the map that it's a function f to f sigma convolving f sigma as a function on R3. Okay, so that's an important simplification that sort of removes the hat from the problem, right? The first problem is oscillatory, the second one is not, is positive, and allows you immediately to symmetrize. Okay, so some of the techniques you were suggesting may apply to this inequality. For instance, if you're looking for maximizers, you lose no generality restricting attention to positive functions, right? The left-hand side goes up if you replace f by the absolute value. With a bit more trickery, but not too much, some ingenious application of Cauchy-Schwarz inequality, you can also prove that maximizers are even functions. Okay? Being even on the sphere just means that f omega equals f minus omega. Okay? So those are two things. Let's say the search for even and non-negative maximizers that are not easy to prove if you remain within the realm of these oscillatory inputs. Okay, but in the convolution world, we can do. So symmetrize, that's one thing you can do. Then, what did Chris and Shaw do? So their main goal was to prove that maximizers exist. Maximizers for this inequality exist, but it's usually not true, right? Because you're looking for a maximum of a unit ball on an infinite dimensional vector space. And to do that, they said something about arbitrary maximizing sequences. Okay, so they wanted to establish the pre-compactness of arbitrary maximizing sequence modulo the symmetries of the plane. And what did they conclude? They concluded, okay, the biggest enemy, pretty much the only enemy to the pre-compactness of arbitrary maximizing sequences is the possibility that maximizing sequences concentrate at a pair of antipodal points. Okay? That's the enemy. Means long paper, 50 pages, hard analysis, but the conclusion of the paper is if you can somehow exclude the possibility that maximizing sequences concentrate, then you win. Okay, and so this picture is meant to illustrate why are these antipodal pairs not an enemy, not a problem. Okay, so what do I have here? There's a left picture and the right picture. I'm trying to explain both. So on the left, this picture here. So we have a sphere. I'm just taking a planar section because the whole thing is rotational invariant. So we have the unit sphere. And the unit sphere has two caps in red, centered around the North Pole and the South Pole. So these caps is what I described here. They're the red caps centered at the North Pole with half angle pi over 4. So you take indicator functions on those caps. And we're going to convolve the corresponding indicator functions, which means we're going to sum the caps. Okay, now it's a geometric problem. You have two caps, and you want the Minkowski sum, the sum set of these two guys. Where is it supporting? Well, it's supporting on the blue region. The blue region has three pieces, north, south, and middle. North contribution comes from 2 points from the north guy. South contribution comes from 2 points on the south guy. And the funny eye-shaped region in the middle comes from a plus-minus contribution. Okay, this is the support of the convolution. Then you have to compute it. It's hard, but you can do it. And why do you do that? You do that to produce the picture on the right. So the picture on the right represents the value of the Stein-Thomas functional for the indicator function of the cap, and it's comparing it with the symmetrized version of the indicator function of the cap. Okay, so C denotes the cap, C star denotes cap union minus the cap. And it turns out that these two guys are multiples of each other. One is like 3/2 of the other. If the angle, or the half angle, it's the same, is not too large. But there's a critical angle that happens here between pi/4 and pi/2. That's like the arc cosine of 1/3, at which point the symmetrized functional shoots off and becomes very large. And this is actually easy to understand from the geometric point of view if you look at the picture on the left. So these caps, what happens when the caps grow? When the caps grow, the blue region is also growing. But at some point, it's growing so much that the north, middle, and south parts, which used to be disjoint, they stop being disjoint. They start to intersect. And that happens precisely at this angle, right? So at this angle, this is when north meets middle, and by symmetry, middle also meets south. And that's when we don't have orthogonality, and actually the symmetrized functional kicks off and is even bigger, energetically even more efficient to concentrate things on caps rather than on single points. Okay. So if you make this picture rigorous, you conclude that concentration at a pair of individual points is not energetically favorable. And so, because of Chris and Charles' detailed analysis, you know that precompactness of arbitrary maximizing sequences is in general. And so maximizers exist. Okay? Of course, they are conjectured to be constants, but their proof even tell us why. And that's what I want to discuss next. Okay? So maximizers exist. We want to know what they are. We conjecture them to be constants. Let's do that. Okay, so here we go. What do we have to do? So it's enough to show that F sigma hat in L4 is less than or equal to sigma hat in L4. So as I normalize F, we have the same algebra as the constant function. This is what we want to do, to prove that constants are global maximizers for them. Everyone agrees? Good. So we start with F sigma hat, and we write it as actually make F sigma hat raised to the third power. And we start by Chris and Charles and write it as F sigma conjunct of sigma in F2 squared. By the way, this starting point should be reminiscent of Gauer's U2 norm that Marius was talking about last week. Right? He said the U2 norm is the only one that can be expressed as the L4 norm of the Fourier transform, and then you start integrating with the parallel calculus and so on. So something similar will happen here. I'm not writing this equals FU2 because it's not the way it was defined. It simply wants a spherical version. Okay, so in order to expand this, we have to know, have a working formula for F sigma coming out with G sigma. We are only interested in the diagonal case where F equals G. And one way to do that is via the following formula, which I think is very useful in computations. So we are integrating. Remember, F and G are both functions on the sphere. So you have 2 points, omega and mu. And as long as the sum omega plus mu equals x, you're good to go. Otherwise, you're not. So that's encapsulated by a delta function, where I write delta x minus omega. And this is the integration over 2 copies of the sphere. Geometrically, we have the sphere. The convolution should be supported on the sum of the sphere itself, which is a ball of radius 2, centered at the origin. So you can take any x of absolute value less than or equal to 2, and you connect it to the origin. Here's a line segment. You locate the point x over 2. You let a plane that is orthogonal to the direction of x go through x over 2 that intersects the sphere on a circle. Let me try to draw that circle. Right? And this circle depends on x. I described it how it is. The center of the circle is the point x over 2. And the only possible contributions to x coming from 2 points on the sphere come from pairs of antipolar points on the circle. Here's one. Okay, so we have the point omega and the point mu. They are antipolar on the circle, and the sum, they both belong to the sphere, and the sum equals x. The picture is not good, but I hope it illustrates what I'm trying to say. Okay, so this picture tells you in how many different ways can I express x as a sum of 2 unit vectors, and that's encapsulated in this. Okay. All right, so we can now expand this guy, use this formula twice, and a FUB. And that will result in the following expression. Let's see if it works. Okay, so what's going on? Each of them has an integral over 2 copies of the sphere. So 2 of them should have an integral over 4 copies of the sphere. I have the product of the 4 functions. And I have 2 delta functions in x, but an integral in x that goes inside. That's what I meant by FUB. And the 2 delta functions become just 1. So what are we looking at? This is not integration over an 8-dimensional manifold. It's integration over a lower dimensional manifold that turns out to be 5-dimensional, consisting of all 4 tuples of unit vectors, which add up to 0. Those are the only points that contribute to this.
But don't you have a different signs for the 2 copies of?
Yeah, so the signs are not really relevant. I'm going to be careless about signs, precisely because of the symmetrization procedure. All these functions can be assumed to be even, and so if I need to flip omega j and replace it by minus omega j, I can do it. Okay? So you're right, I should be careful about signs, but I'm not being careful because all functions are equal.
And that's not influential to the initial derivative.
Correct. Yeah. All right, so I have this expression. And what's one tempting thing to do? I mean, we start with the Cowers again. We should do Cauchy-Schwarz. Right? What happens if we do Cauchy-Schwarz? So I do Cauchy-Schwarz with respect to this positive measure, which is this sigma. The product of this sigma is times delta. It's a positive measure. And I do Cauchy-Schwarz, so I'll get the geometric mean of 2 integrals. Both integrals are the same by symmetry. So I'm just going to write one of them. So that's the integral f squared omega 1, f squared omega 2, delta omega j. Now, this only depends on omega 1 and omega 2, so I'm going to integrate in omega 3 and omega 4 first. And I'm going to abbreviate. So this just means d sigma omega 3, d sigma omega 4. And the d sigma omega 1, d sigma omega 2 are upside. So I have 2 copies of the sphere here and 2 copies of the sphere. Okay? This is just by Cauchy-Schwarz. I'm using Cauchy-Schwarz with respect to this underlying positive measure. Okay, but what can you tell me about this inner integral? Have you seen anything like it before? How can I write it in terms of the objects that I define? This guy is not so different from this, right? They are both integrals over 2 copies of the sphere. Okay, the functions are not there, that's just because they are constantly equal to 1. And x is the point omega 1 plus omega 2. So this is sigma congruent with sigma at the point omega 1 plus omega 2. Again, I'm not worried about sums because I can always root the sums. Okay, so we have to know what this is. we have to compute the convolution of surface measure on the sphere.
Very good. So you can flip the sign of each variable. So you can just have like minus 9 for the one variable if you want.
What's the question?
So you can flip the sign
You can flip the sign.
in each variable.
Yes, independently.
Okay, right.
Okay, so now we have to compute this convolution. And there's many ways of computing it. So let's compute sigma involving sigma. So one, I guess, more or less obvious way to use free inversion. We just know that sigma hat is some Bessel function. In this case, it happens to be an elementary function, it's like the sinc function. So you have to square it and fully invert that. You can do it, it's a long, bit tedious, not very inspiring computation. So here's a better way to do it. Let's not use the Fourier transform, let's remain in physical space. We want to compute this down. So we can pair it with a radial function on R3, integrate, and try to compute this. Okay. So we use the definition for sigma convolving sigma in terms of delta functions. It's on the board up there. So that's delta x minus omega minus mu. This is omega mu. Dx. This is two colors. Student and this is. Okay. All right. Now we can use the B. So integrate over S2 cross itself first. Dx comes in, and you're doing a dx with a delta function. So actually, you're computing phi at the point on the vector constant, so maybe a function. Right? Is deltas are 1, which is good. Now we have two spherical integrals. We can pick one of them and compute it in spherical coordinates. Okay, so I'll keep one of the S roots, let's say the one with mu, and the omega I evaluate in spherical coordinates. So it's interval from 0 to pi, interval from 0 to pi. T of this guy, well, this guy in spherical coordinates will be square root of 2 plus 2 cosine phi. Phi is the latitude angle. Remember, both omega and mu are unit vectors, so we get 2, and then the inner product between omega and mu, that's what I want to do cosine phi. Okay, so 2 plus 2 cosine phi. There's a Jacobian factor, sine phi d phi. The phi varies between 0 and pi, that's the latitude. Then there's a theta that actually comes out because it doesn't work in this rotation area, and the sigma. Okay. All right, so this whole thing equals 2 pi. That's the contribution of the b theta integrand, nothing depends on b theta. And then I can change variables. I can call the square root of 2 plus 2 cosine phi. I can call it r. So when phi, sorry, the phi is they're supposed to be the same. When phi varies between 0 and pi, r varies between 0 and 2. So I'm going to do 0 and 2. I have the outside interval over S2, and I got rid of the interval from 0 to 2 pi because nothing depending on there. And then like that, I have theta r, and the change of variables tells me that sine phi equals r d. Okay. All right, but this thing here, I can write it as an integral over R3. How? Well, the integral over R3 in polar coordinates will have a Jacobian R squared theta, so it's equal by R. Okay, and this whole thing becomes the integral of phi, it was a radial function of 3, of what? 2 pi over x. Yes. And this is an integral over the whole of this full separable field. This is true for any radial function. So this guy should equal this guy over this sigma. And the conclusion is that sigma convolved with sigma, which is up there, is just 2 pi divided by the length of omega 1 plus omega 2. So I would really like to go back there and put it as it goes. But I think I will still do it. Because I just want to highlight the fact that what we've done is not going to leave us any. So we were here. Now we know that this guy is 2 pi over omega 1 plus omega 2. And what you have is a double integral on f squared, so f squared omega 1, f squared omega 2. The 2 pi doesn't really matter, divided by omega 1 plus omega 2. Okay, there's no way that this thing is bounded by the appropriate power of the autonomial. Okay, it's just not true. This is not bounded by the autonomial of the. And one way to see this is, okay, you have a singularity here. This blows up by omega 1 equals minus omega 2. And so if you take x that again look like, I don't have the picture anymore, but x that look like this. So if they are concentrated on a pair of integral points, this guy is just going to be too large most of the time. Okay? And you can make this with this. So we've lost the moment we decided to do this Cauchy-Schwarz thing. Okay? We did this naive Cauchy-Schwarz, and that's too late. We're not even going to recover the non-sharp time dots. Let's not even talk about optimal constant. Even with any finite constant, we just don't need it. Okay? And I believe this was Christensen's theory. Okay? This is like all of this is sort of implicit in their analysis, and they couldn't continue because of this issue. Any questions so far? How much time do I have?
20 minutes.
20 minutes. See how I do this, okay? Okay, so we need to gain the form of a magical identity by asking who in 2013 observed the following. So the thing we're trying to estimate, this L4 norm of f sigma hat, is expressed in terms of an integral with a delta function, and the delta function says we only have to look at 4 tuples of vectors that sum to 0. Right? Okay, so for these guys, you have 4 unit vectors that sum up to 0. There's something special that you can say about this one. Omega 1 is omega 2 squared. Omega 2 is omega 3 squared. Omega 3 plus omega 1 squared. What is this? Well, you can expand and you get about 6 unit vectors, norm squared, plus twice a certain quantity. I'm calling x, and the quantity is just the sum of the pairwise distinct inner products. Omega 1 dot omega 2, omega 2 dot omega 3, omega 3, omega 1. Okay, these are unit, these are dot products between unit vectors. Okay, so if we find the value of x, we find the value of this. And how to find the value of x? Well, another observation is that if the 4 guys sum to 0, 3 of them have normal. Because these guys equal minus omega 4, that's also a unit vector. Okay, so you square. And what do you get? You get 3 unit vectors plus twice x. So x is necessarily -1. So this guy equals 4. Okay, this is a nice observation that sort of comes out of nowhere. I'll try to motivate it later on, but it sort of allows us to make progress on the problem. Reverse. So 1, 2, 3. Sorry about that. All right, so where are we? F sigma height in a form. Instead of writing it in this way, which is not good for Cauchy-Schwarz, we've seen that it fails, we can use the magical identity to write it as B form times the same thing, but with this extra term. Omega 1 plus omega 2 squared. Delta. Delta. So what did I do? I just used the fact that this integral is over 30 of the unit vectors which sum to 0 to invoke Cauchy's identity and write 4 in a creative way. I'm just writing 4 up and down. 4 is omega 1 plus omega 2 squared plus another guy plus another guy. By symmetry, all these three integrals are the same. So we can pick up the contribution of 3 with that effect. Okay. All right, and so here we can try the same trick. We can try Cauchy-Schwarz, but now it's better. The same Cauchy-Schwarz after this magical identity is the uniform. Omega 1 plus omega 2 squared. X squared omega 1, X squared omega 2. And then the same convolution that we computed, sigma convolute sigma at the point omega 1 equals omega 2, which is 2 pi over omega 1. So okay. And this is sigma 1, 2. And now this guy cancels with 1 power here, and you're left to analyze this bilinear form on straight. So an indication that we're on a good path is that this already implies if we don't care about sharp constants, we have a proof of Stein Thomas. Right? Have a proof of Stein Thomas because both omega 1 and omega 2 are unit vectors. So this is at most 2. So if you lose a factor of 2, 3 over 4 and 2 pound, you bound this by the L2 moment. Right, the appropriate power. Okay. So this already implies non-sharp Stein Thomas. We need one more step to get the sharp version. Okay. And I have prepared, I guess, 1/4 of a blackboard to tell you why this magic identity is not so magical at all. After all, sorry. But since I'm running a bit short on time, I will leave that for questions if you're interested. Okay, so there's an alternative approach to this step that does not use Cauchy's observation. If you want to know, just ask. All right. So recap. Where are we? So we need to find a coordinate one from that on the sphere, which is very close to the real omega 1 plus omega 2 squared, the deltas of the sum of the vectors and the 4 functions. And by see that it's not whichever F1 x squared 1 down is like an orbital on the diagonal. Right? If we do that, we're good. Remember, that's what we wanted to do. This is my first enough to show. Right? Okay, so how do we do that? We have f squared, and we write it as the sum of the constant function 1 plus a mean 0 function. Okay? So G has average 0. This is, remember, similar to this trick that Mario taught us last week with balanced functions. Like sometimes it's very important to consider balanced functions from the very beginning. Balance means zero average. And once we have that expansion, we can just use a multilinearity to expand. Like each x squared replaced by 1 plus g. You'll have 4 terms once you expand. One of them is precisely 1 but 1, 1, 1, 1, which cancels with the guy on the right hand side. Then you have 2 terms which have just one appearance of g, but so it's 1 the g 1, 1, 1. But since g has mean 0 and everything else is radially symmetric, those contributions are 0. So we're left with 1 term, which is 1 over g 1, 1. And we're going to check that this is what it is. Okay. So that's our mission. That's what I would like to do next. Is it clear what's going on? So x squared divided in this way. You have 4 terms, so 2 of them are 0. The other equals exactly what's on the right hand side. So you just have to check that the remaining term has the correct. Okay, and so how do we do that? We define a certain family of distributions, of homogeneous distributions, and we try to interpret this as that distribution acting on a particular sufficiently dense function. The family of distributions I'm talking about is HS. So it's homogeneous, so it's standard. It acts on a Schwartz function. So let's say that phi is a Schwartz function, and there's a normalization factor in terms of the gamma function, and then you put x equal s, e, or x equals. Okay. So this makes sense if real part s is a complex parameter. So if real part of s is greater than -3, this is what we find. This is what we interval 3. Then it's a homogeneous distribution of degree s, and the gamma factor is here, so that the Fourier transform behaves like that. So with this gamma factor in front, hs hat equals h minus the next s. Okay? So the Fourier transform of homogeneous distribution of degree s is homogeneous and it has degree minus e minus s. But in this case, these are distributions on our field. Okay? But I want both of them to be like totally integrable, so this makes sense. If real part of x is greater than -3, and real part of -3 minus s is also greater than -3. So that means that s is in a strip. Real part s should be found between 0 and -3 and from above +3. Okay. Okay. All right. So why am I telling you about this distribution, this family of distributions? Because this guy we have it completed. Right? So this is this guy equals the integral of omega 1 plus omega 2 squared. G omega 1, G omega 2. And then the deltas, which get integrated in omega 3 omega 4, that produces sigma over sigma omega 1 plus omega 3. Is sigma 1, 2. Again, this guy cancels. And what we have is basically a homogeneous distribution H1 acting on the function G sigma from voltages. Okay? That's the connection. That's the reason why I introduced this status, is to be able to write this thing that we want to prove is non-positive as homogeneous distribution H1 acting on the function G sigma for voltages. Okay. Now we can use pleasure. So this should be the same, maybe I'll continue if that's okay. So this should be the same as H1 hat acting on the Fourier transform G sigma over G sigma. H1 hat is H minus B minus 1, H minus 1. H minus 1 acting on the Fourier transform of the convolution, which is a product G sigma hat squared. Any complaints about what I'm doing here? What about the gamma function? So the gamma function is there just to ensure that this formula is correct. But I told you that this formula is correct on a certain range. Both 1 and -4 are outside of that range. So this will be a problem,
Sorry,
but it's not.
this is H hat or, you know,
Yeah, H1 hat. H1 hat is H -4.
which one hat?
Right.
Very good.
H is H -4 because it's.
Mhm.
But the problem is that neither 1 nor -4 are in this range. So what's going on? Is this really a problem? It's not, because we are not applying H1 to a generic Schwartz function. We're applying it to a function whose Fourier transform vanishes at the origin. That's where we use once and only once the assumption that G is balanced. G has integral 0. This is the same as G is sigma at the origin. Okay. So since that's the case, you can actually make do with higher orders of integrability, and this is okay. All right, this is okay, but it uses strongly the fact that G is sigma higher. And now the gamma, I don't know who asked about the gamma function, now it enters the picture, right? Because this guy involves a positive quantity, but then you factor gamma of -4 plus 3/2. That's gamma -1/2, which is a negative number. Okay. So this is negative or non-positive because gamma of -1/2 is negative. Okay. So that's a proof. We proved that this guy is non-negative, which means that this is correct. Which means that F sigma hat in L4 is at most sigma hat in L4 if both F and 1 are non-negatives in the same. Okay, how many minutes?
5.
5. All right, so what to do in these last 5 minutes? Actually, you can tell me what to do. I have a few alternatives. So again, the same way as I told you that magic, that Foski's magical identity is not so magical. At least we have a conceptual explanation for that. There are also alternative ways to this last step. Okay, so this last step here can be done both with spherical harmonic decomposition. This was Foski's original approach, or with a sort of a method of rotations. Which goes in the direction of the methods you were suggesting. So it's a sort of a subtle rearrangement that works in this case. And so the whole proof, we have it all on the board, consists of 3 steps. There's a first step, 3 ideas. There's the first step that is either Foski's identity or this alternative that I proposed. There's a crucial Cauchy-Schwarz step that, well, that's the wrong Cauchy-Schwarz, that's the correct Cauchy-Schwarz. I don't know of an alternative for that step. I wish I could, I got it, but I don't. Cauchy-Schwarz is just Cauchy-Schwarz. And the third part, which involves some sort of spectral decomposition or analysis of homogeneous distribution. Okay. So if anyone's interested, I can talk about any of these alternative approaches. I can also give 3 more comments. So that's the proof that constants maximize L2 L4, but of course it doesn't give you a full characterization of the maximizers. Okay, so that's also known. Maybe I will comment here. Yeah, so we have what we do. We prove it's in with the optimal constant, but we call it CST for 1 minutes. L2 S3. So it turns out that F gets S squared. So it turns out that F maximizes ST squared if and only if F is a character. So that means complex constant times E to I C dot omega A is a non-zero complex number, and C is any vector unit. Okay. So of course, if C is the zero vector, you get constants, and constants can be any constants. And the appearance of these characters, they come from the symmetries of the equation. So if you think about symmetries of this equation, someone mentioned that it's the rotation invariant. Of course, it's rotation invariant. But if you replace f by f and move the rotation and s with 3, you don't change neither side of inequality. That's a compact group of symmetries, so not so exciting. But there's also modulation, right? You can modulate f, which means multiplied by a character of this form, which means that f sigma hat will correspond to a translation. So again, both the left and the right hand side are preserved. And this modulation group is non-compact because C can be any guy in R3. Okay. So proving this is hard work. That's another paper, Crystal Sharp. But it was done even before one single example of a global maximizer was discovered. So now we know it. There's also, so that's the first comment. There's also a sharpened version of time Thomas in the sense of quiz, so quantitative stability that's not constructive, which basically says that CSP, the best constant squared, F L2 squared minus F sigma hat L4 squared is bigger than or equal to some constant, positive but implicit, we don't know what that is. FC, and so this is the distance of f to the space of characters, functions of this form, right? If you're a function of this form, this distance is 0, you cannot do better than the sharp inequality, but if not, you can. And this was first observed. I mean, it follows the usual scheme, so you have complete characterization of maximizers plus pre-compactness of arbitrary maximizing sequence. So this follows the Bianchi scheme. And this was observed in a paper. It was published in 2017. All right, and last comment for the slide, which is what happens in higher dimensions and other exponents. Okay, that's my last slide, and that is my last comments on this for today. So everything we've been talking about so far is about this one here, right? We're in, this dimension corresponds to the dimension of a sphere, not the empty space. Okay, so this is S2, and we were talking about L2, L4, or S2. So this guy is known in sharp form. Here's the proof. Some variant of the, I mean, I told you that the proof is flexible, right? I mean, certain steps we know with many alternatives. So if you carefully choose the alternatives in each step, you can make the proof work all the way up to dimensions 8. Okay, I'm talking about L2, L4, on S2, S3, S4, S5, S6. Okay, that works. Of course, in higher dimensions, it's not so interesting because it's not endpoint anymore. As a matter of fact, the dotted lines, they represent the Stein-Thomas, the endpoint Stein-Thomas lines. And we care about this algebraic situation in which exponents are even integers, and there's not very many. This line does not intersect the even lattice in higher dimensions. Anyways, the proof basically goes through. With a lot of additional work and many different ideas from probability, lead theory, and calculus of variations, we were able to extend this on the same set of dimensions to higher degrees of multilinearity. So if instead of L2, L4, we want an L2, L6, or L2, L8 sharp inequality in these spaces, it absolutely does not follow by interpolation because we're looking for sharp constants and maximizers. And there's a bootstrapping procedure, rather indirect, that allows you to take the starting point L2, L4 and conclude that characters continue to be a complete set of maximizers on this. Okay, so black means solved. We know what the sharp inequalities are. There's an interesting question for higher dimensions because all the methods seem to fail. And there's a particularly tantalizing question in dimension 1, so that's for the circle in R3, where the endpoint Stein-Thomas is 6, not 4. The conditional result still holds. So if we knew that characters are unique global maximizers at this point, we could bootstrap it and get it for L8, L10, L12. But this is an open problem. I believe Valentin is going to tell us about it on Friday, right? A bit Okay, so stay tuned for the problem on this one. And last comment, so you see that there are some funny symbols here, I have a cross and a circle. That just means that in those dimensions of the exponents, a similar inequality holds, not on the sphere, but on the full paraboloid or the full cone. And that's the topic for today. Okay. So maybe I'll finish with just a list of problems. This is a list of open problems that I selected for the whole week. Boldface is what's about today's lecture. We'll talk about non-boldface tomorrow and on Thursday. So I have three problems that I think are good problems. The green, yellow, and red, you probably guess what that means. So a green problem would be to get sharpen Admon form on other manifolds, not just spheres. This is quite even higher codimension spheres in open. I think that's quite a tractable problem and very, very interesting because fun stuff happens. A bit more ambitious would be to break this dimensional barrier. I told you that the proof works until dimension 6, but then all of them just fall apart badly. I think there's a new idea that's required, but I don't think it is too much outside of mankind's reach. A hard problem is the endpoint L12.6 on the circle. Okay, so maybe this is a good time to start.
Okay, thank you, Joe. Okay, so here the point is that noon we have a seminar, and maybe just to rearrange everything. So I don't know if maybe a good idea just to have discussion in the lunchtime, or maybe tomorrow to the start, we can start a bit earlier with questions by the people today.
Sure, as a
According to your lecture, and then I mean tomorrow we have an hour break as well.
Just like today.
Yeah,
right.
So maybe we can start at 5-10 minutes as anyone who wants to discuss something from the and then
Sure.
Is this okay? Or
I'll also be
the rest of the organizers
I'll also be around for lunch, so if anyone wants to talk.
because the other one will be a bit.
Sure.
Okay, thank you very much. See you tomorrow.
See you tomorrow.